Architectures for cloud applications. So, a quick recap on software architectures before we begin. We can define software architectures in different ways. We can start with the basic boxes and lines. So we draw on a piece of paper, we draw a box and say that this is a component, and we draw a line to another component. And we run into the usual problems with that type of definition, that we don't know what a box means and what a line means. We can add semantics. We can explain in a legend that this is the meaning of this box, this is the meaning of this line, and the fact that we've placed these two boxes next to each other means that they are related in this and that way. Or we can go with the definition that the Software Engineering Institute provides, which is that the software architecture is the structure or structures of the system consisting of software elements, externally visible properties of those elements, and the relationships among them. So there are a few keywords here that we are looking at. Software elements, those can be components, can be modules, can be hardware units, can be threads, processes, or whatever. But software elements. We're not looking at what's going on inside of those elements, but we're looking at the externally visible properties of those elements. And also we're looking at the relationships among them. So how do these different elements cling together and fit together to build up your application? Another way to look at the software architecture is that it consists of the decisions we make. So we identify at some point that we have a particular issue, and in order to address that issue we need the following components and the following relationships between those components, and therefore those components and those relationships are merely an instantiation of those decisions that we make. So in that sense the software architecture is the decisions we make and nothing else. We can get influences on the architecture from different perspectives, from different directions. For example, the customer requirements, which is obvious. If we need to solve a particular task, we may need to have a certain number of components to address that task. But also the developing organization. For example, what organizational units do we have? What experience do we have? Maybe we have contracts in place that we need to buy certain pieces of software and plug it into our system already. And the technical environment. What development environment do we have? What platform do we have? And what cloud platform, for example, do we have? All of this influences what we will decide to do in our software architecture. And a good software architecture, it's based on conscious decisions. So we actively identify the places where we need to decide, and we take those decisions consciously and well informed. We evaluate the architecture to make sure that we satisfy the goals necessary. We pay attention to current and future quality attributes. So what do we need of the system right now, and what may we need in the future? We document the architecture so we can trace it to the architecture decisions. So when we look at a particular component, or we look at a particular relationship between components, we understand why that relation exists and why it is defined as it is. We have well-defined modules with well-defined interfaces and well-defined responsibilities, so that it is clear what the architecture is, or each element in the architecture is supposed to do. And we have a small set of interaction patterns that we use consistently. So rather than having each component talking to each other component in a novel way, we decide upon a small set of communication channels, and we stick to them. A software architecture can be defined in many different views. So Basetal has a module, component and connector, and allocation views. Christian has a logical view, development view, process view, and a physical view. Hofmeister, which I tend to use a lot, has a conceptual view, which is nothing about how we're going to build it, but it's our conceptual understanding of the components we need. The module view, which is our definition that this is the software modules that we're going to need in order to satisfy this conceptual view. And the execution view, which is how we're going to allocate those modules to our hardware. And the code view, which is how we're going to allocate these modules into development units, so files, packages, etc., etc. And this together, all of these must work together to make a whole architecture. We can't just focus on one of them. And it's relatively easy especially when you look at cloud computing, that we focus on the execution view. We focus on that we can add new servers and we can throw more hardware, more virtual hardware at the problem. But we still need to address the conceptual view. We still need to address the module view. And if we're going to develop this large scale, we also need to address the code view. Quality attributes is at the core of software architectures. Functionality is, as Jan Bosch once said, it's easy to implement. Anyone can do the functionality, but getting it with the right service level, with the right quality attributes, is what's difficult. We may sometimes solve our quality requirements in the implementation, but more often it's in how we structure the system that we address the quality requirements. But the architecture, I should point out that the architecture can only give you a potential for satisfying a particular quality requirement. You can have the best architecture in the world, and then you can, with less than optimal developers, they can squander that opportunity, or you can have brilliant developers who can get the quality requirements in place no matter what the architecture you give them. So the architecture gives you a potential, makes the life easier or harder for your developers. There are different factors that push you towards the cloud with different impact on your software architecture. So one of the factors that you may have is transference, that you have an on-site solution, and for example, for economic reasons, you've figured out that it's cheaper to go to the cloud, or your boss has. You need to transfer your existing solution to a cloud platform. A challenge here is to set up a similar environment in the cloud as you have locally, with the right libraries in place, with the right development environment or deployment environment. I ran into problems recently with this because I was helping a student, and the student ran into one problem, and I had to do a lot of cleaning up on my system just in order to get to the place where I was experiencing the same problem as the student, because I had more dust in the corners. Things worked differently for me. So just assuming that because we start from a clean install on our cloud server, things will be easier, that's not true. The clean install might actually be harder to work with as well, because we have dust in the corners, if you will, that will help us in some sense. Another factor is if we scale up to handle more users. If our user base grows and we need to scale up, just going to the cloud, we will probably have the same bottlenecks as before, for example, the database design. So we need to rethink our architecture, rethink our software solution in order to make best use of the cloud and the fact that we now have more hardware resources available. Slightly related, if we have large swings in capacity requirements, so that we may have a planned situation where we have a lot of work to do that we wouldn't want to do overnight, for example, recompute all our product catalogs, for example, recalculate our product catalogs, and we do that nightly. Then this is called burst compute, and what we need to do then is to make sure that we are able to take care of this burst compute. Can also be that we suddenly get an uprise in the number of concurrent users. An event happens that means that we get hit by more users. So we need to do load balancing to take care of this, so that our application actually is able to support this swing in concurrent users. Accessing the database might be a problem again, and we need to deal with this. And if our application scales up, not necessarily with many more users, but with much more data, we need to start looking at where is this data processed. and how can we speed that up and make it more efficient. Some quality attributes relevant for cloud computing: scalability, reliability, availability, performance, security, privacy, cost optimization, and maintainability and developability. So let's go through these quality attributes one by one and see how we would think about them, what are the challenges, and what can we do about them. I'll be talking about Architecture Tactics, which is from the Bass, Clemens, and Kasman book. It's their templates for solutions for architecture problems. But the most important thing here is that you start thinking about how to address these issues and how to address these tactics in the software architecture. Not just in terms of throwing more hardware at the problem, but also which components do we need, which connectors do we need, how do we need to configure those connectors to actually address the underlying problem. Some of the course books, the Cloud Architecture Patterns in particular, are a useful read to give you pointers on how to think of your software architecture to address these issues. Starting with scalability. Well, we can talk about two types of scalability. We can talk about horizontal scaling and we can talk about vertical scaling. So horizontal scaling means that we add more nodes. We throw new virtual machines at our problem or machines. Whereas in vertical scaling, we increase the capacity of the nodes. We increase the CPU speed in them. We add more cores to each computer. We can do a bit of both in a cloud system. It's easier to do vertical scaling because we don't have to worry about communication between different machines. But if we have something which is already horizontally scaled, then it's probably easy to just scale more in that direction. There may be limitations here in your choice of programming language, actually. So doing vertical scaling with a Ruby application can be a bit of a hassle, for example. Tactics for dealing with scalability. Actually, the Bass, Clemens, Kasman book doesn't have any tactics with scalability, but performance is sort of related, so we can look at those. We can control resource demand so that we limit the number of jobs we can get at one point in time, and then we can manage our resources better so that we use the hardware we have and we make sure that we have resources available to the number of jobs coming in. And that's basically what these specific tactics say: manage sampling rate, limit event response, etc., etc., etc. The big thing to remember here again is how can we support this in the software architecture. So when we say increase resources, yes, that's going to mean probably that we add a new virtual machine. But how do we use that virtual machine? Do we have a load balancer up front that distributes the jobs to these different virtual machines, or do we set up the new machines as worker nodes that go to a queue and pick jobs more or less autonomously? Two very different approaches to the same problem. One is push, the other one is pull. So we need to think about the software architecture when we decide which of these tactics we're going to use. Reliability and availability. The primary tools we have here is redundancy, that we add more machines doing more or less the same thing. We can distribute between different places in the world, different providers, so we can have our system running over many cloud providers. And then we do load balancing between those different servers that we now have up and running, possibly on different cloud providers. When we have a cloud solution, we can do a trade-off between programming reliability and making sure that our system will work as expected, and throw in redundant servers. So basically, if we know that our system might go down, well, we can throw in a redundant server rather cheaply. There is a trade-off here when the development time to make program a reliable application is more expensive than just keeping a redundant server up and running to take over when, in those instances, when the application isn't functioning as expected. Data persistence is connected to this. We don't know when or how our node will be shut down, if it will be shut down in a tidy way, or if someone will just cut the power to us. So if we're in the middle of a job and we want to resume that job when we get the power back again, we need to make sure that we have some form of data persistency. Availability tactics. Three main categories. We can detect the faults, and we can recover from the faults, and we can prevent the faults. There's a bunch of different things we do for detecting the faults. We can ping our servers to see if they're up and running. We can keep monitoring on them. We can ask them to send heartbeats to see that they're still alive. When they send messages, we can look at timestamps to see if we get the timestamps in the right order, for example, and so on and so forth. Once we find something that's not working as expected, we can prepare and repair, and then we need to reintroduce this faulty machine once we fix the problems. Prepare and repair has a number of different tactics underneath it, so we can either we have servers always running in parallel, running in tandem, doing the same things, and if one of them breaks, the other one is able to take over immediately, or we have servers running idle waiting to take over, or we have servers that aren't up and running but they can be booted up quickly to take over. Exception handling, rollbacks, and software upgrades, etc., are different ways of dealing with recovering from a fault. And once it's time to reintroduce the server, we need to take over again from the backup solution that we had, which is not a trivial subject either. And then preventing the faults can be done in a number of different ways as well. And I remind you again, which of these would be relevant in a cloud application, and what can we do to support this in the software architecture? Performance is not just one quality attribute, it's a whole bunch of them. And the way we deal with them differs very much depending on which one we're after. For example, response time is very different from processing time, which is again very different from storage capacity, and all of them go under the umbrella term performance. And you're going to have a mixture of many different quality requirements with relation to performance. So you may need to do a trade-off here. For example, with storage capacity, you may go for a slower storage on your cloud provider, Glacier, for example. But that will make your response time slower for those instances when you need to go to that slower storage. So there's a trade-off to do here, and which trade-off to do is depending on the application, obviously. A few examples here. If we have a web application, well, response time is one requirement that we must be able to use the system, and web users don't have that much patience for a spinning beach ball telling you that the system is loading something or processing something, so it must feel snappy. But on the other hand, behind the scenes, activities may take longer to perform. So for example, if you submit a post in a discussion forum, in a modern discussion forum, that may include rebaking the user profile, looking for crossed posts, rebaking these posts because with the new information that someone made a reply or someone mentioned this other post somewhere here, regenerating thread summaries, etc., etc., etc. So this may actually take up quite a bit of time. And if you have a complex enough forum with many threads, many posts, many relationships between those threads and posts, this will take time to do. So how do you then make sure that you have a snappy feeling to the system, that it reacts immediately, and yet have all of these things happening behind the scenes? At the other end of the spectrum, we have batch processing applications, for example, Cloudbursting. So you use the cloud computing resources to generate or regenerate massive amounts of data. Most of the time here, response time isn't an issue, but throughput might be, and storage capacity might be. So this is a completely different set of requirements for this type of application. In terms of performance, I've mentioned them before: control resource demand and manage resources. And again, what can we do in the software architecture to deal with these, or to address these tactics, or use these tactics? Security can be divided into security from external threats and security from threats inside the cloud provider. External threats are the obvious ones that we normally think of, that someone from the outside is trying to hack our system, break our system, or use and abuse our system. Inside the cloud provider, since we are sharing our machines, our virtual machines, with a lot of other users, there might be covert channels between our virtual machines and others. There might be ways to sniff network communication, and the design choices that the cloud provider makes, for example with their storage facilities, might be inherently unsafe. There might also be legal issues involved here. So security has many different ways of showing up its ugly head. There are basically 4 steps or 4 ways to address it. We can detect attacks, and we can resist the attacks, and we can react to the attacks, and we can recover from the attacks. So detecting the attack means that we detect that someone is trying to intrude into our system, or that someone is trying to prevent us from providing the service, a service denial, or someone is trying to spoof messages into the system, or in some other way attacking us with the help of the communication channels that we provide. What we can do is we can make sure that we have good authentication and authorization in place. We can limit access and exposure, not only in terms of that we limit it to a certain set of users, but also in terms of firewalls, that only certain ports are open, for example. So these are standard ways of dealing with it, dealing with security. Encrypting the data to make sure that even in these unsafe Amazon buckets, we can use them, but no one else can make sense of what we have there. Changing default settings is an interesting way to address security. In some way you would say that that's security by obscurity, but at least you can't use the default passwords to get in. And when we identify that we are being are being attacked, we can lock down the computers, we can revoke access from a particular user, and so on. And recovering it means, first of all, that we need to understand what happened, and then being able to restore. And we run into the same problems that we had during availability to reintroduce an attacked machine once we have cleared up the attack. Privacy is extremely important in a cloud solution. simply because it's so many things that are no longer inside our control, so we need to worry more about it. And the easiest way to get bad publicity is to neglect privacy issues. They are often regulated by law, and mind you, these are local laws, so they may differ from different countries. And privacy also ties in with security, because with low security, it's harder to enforce privacy. This is one area that Bas Clemens-Kasman don't say very much about, but generic guidelines include that we limit stored personal information. Unless we need to store certain information about our users, there's no need to do it. Try to limit how much information you store, and try to limit for how long you store that information. That will help you circumvent many of the privacy issues. Encrypt the data that you have, use secure connections, and hire a lawyer. This actually is a cost optimization. If a lawyer is able to determine that you don't need, for example, to store data about your users in each country in the European Union based on their local laws, but you can have them in one place, that's going to save you a lot of money, which will pay for the lawyer. Cost optimization. Well, I mentioned this before, but there is a trade-off between just looking at the raw figures of cloud computing and saying that, see how much cheaper it is to use a cloud platform rather than using our in-house service, and the fact that with smarter development, you may not need to the same number of resources. So just throwing more service at the problem is one way of dealing with it, or thinking about it and solving the problem in a different way is a different way of addressing the same issue. But there's a trade-off. At some point, your development effort is going to be more expensive than just throwing more service at the problem. Maintainability and developability. It's not a cloud issue in such, but it becomes more obvious when you're actually paying for every minute that your servers are up and running. So this problem space is that each of your developers need a development platform as usual, and you need a test environment. So do you have one test platform per developer, per team, or whatever? You need different test environments for different types of platforms. If you've got a Windows platform, you need test environments for that. If you've got a Unix platform, you need a test environment for that, and so on and so forth. And there are different ways of providing this. Either you do it with local virtual boxes on the developers' machines, or you do it on the cloud. If you do it with local virtual boxes, then each developer needs a more powerful machine. And especially if you want to have a meaningful test environment with a significant amount of data to play around with. Staging environments should be as close to your deployment platform as possible to do the release testing, to iron out the last problems before you actually deploy. And how many staging environments do you need? Is one enough? Or do you need more? And how do you test the system once it's in the staging environment? You're probably going to need more servers to actually run your tests against this staging environment. And then you have your deployment environment. Is it just one, or do you have one per customer? How do you scale this? So that if you get more customers, or if you get more concurrent users, you need to scale it up and down, all of the regular cloud issues. But how do you reflect this scaling strategy in your staging, testing, and development environments? So since all of this fits together, you need to think about your final solution, your deployment environment, and model your staging environments, your test environments, and your development environments in a similar way to actually, so you have actually tested and developed for your ultimately your deployment environment. Also related to this is that how do you support these different environments? How do you construct your applications such that it can be deployed into the test environment, into the staging environment, or into the full deployment environment seamlessly with a one-click solution, preferably. And how do you construct your application so that you can actually run automated builds and tests in a quick and easy way? So in summary, there are quality attributes that are more relevant than others for cloud applications. Your first stop is to figure out which quality attributes are relevant for you, and which of them are more important and which of them are less important. And then you design your cloud application similar to the way you design any other application, but you pay more attention to the execution view because that's where you get the main benefits from your cloud environment. But because you pay attention to that one, that means you also need to pay attention to your module view and, in the end, your conceptual view. Pay some extra attention to privacy because this is a really relevant issue for cloud deployments, and pay some extra attention to your development environment as well because it is more complex with a cloud solution.